All right, good morning. Thank you all for coming. We can get things started with our first talk. Enjoy.
Hi everyone, welcome to the talk. My name is Palak Bansal. I'm a graduate researcher at NYU. I'm actually graduating tomorrow. And I have a background in computer science, and me and Hoa will be talking about our graduate research here.
Yes, hi everyone. My name is Hoa. That's it. My name is Hoa. I am also a graduate researcher, also graduating tomorrow. And thank you all for being here, and welcome to our talk about GANs for Causal Inference. Our project is done under the guidance of Professor Elena and in the Department of Economics, and Professor Pedro in the Department of Economics as well. I forgot to mention I have a background in economics and math, and our project lies at the intersection of computer science, data science, and economics. So before we dive in, I want to talk a little bit about the introduction to causal inference. Are you all familiar with causal inference? Maybe show of hand if you are. Yeah, I think so. As you probably already know, causal inference is to establish the cause and effect relationship, and from then we can infer the effects of any treatment or policy or intervention that we have. To do so, we need to focus on treatment effects, which is the individual difference between the outcome had one been treated versus their own outcome if they had not been treated. The key here is that it's their own outcome. It's not somebody else's outcome. It's not their outcome under some other circumstances. So in mathematical terms, it's y1 minus y0. And you probably will see a treatment effect under the term ATE, average treatment effect, which is individual treatment effect, average over the entire population, or average over the treated or non-treated individual, which make it ATT or ATC. Let's talk a little bit more about why we need to focus on their own outcome. So let's take an example about after school. A very basic example, but would help us to get there. So let's say that Joe struggles at math and he participates in an after school program. Let's look at, if this is Joe's math score, before the program he has 65. And after the program, he has 55. So the question is, does it mean that the program makes him perform worse than before? Do you think that means that? Or do you think the program is not very helpful? Anybody thinks that the answer is yes? Obviously, well, not, right? Because the second test would be a lot harder. There are many other things that could have changed when he takes the first test versus when he takes the second test. So then let's focus on the second test only. If we look at the math score after the program only, focusing on Joe who took the program and got the score of 55 versus Jane, somebody else who didn't take the program but got the score of 75. Then would you say that this program makes Joe perform worse than Jane who didn't take the program at all? Well, who thinks the answer is yes? Not, right? Because Jane would be a lot more comfortable with math in general. So that means that there are other covariates that could go into this question. The covariates such as like whether their parents are very invested in their education or not, whether Jane or Joe have been taking other classes outside of this program or not, or some other covariates common in cases we can find like age or gender or race. So that brings us to the fundamental problem in causal inference, is that to establish the causal effects usually requires a comparison of counterfactuals, so the outcome under treatment and under non-treatment, given that they have the same covariates. However, this is very highly unlikely in reality. You will probably not find someone else who is exactly like you. I would be sad, or I don't know how you would feel, but I would be sad if someone else exactly like me. Makes me not very unique. But that brings us to the fundamental problem. Because we can only see, there are usually two potential outcomes, but you can only observe one. So if only there is a way for us to fill in these question marks, wouldn't that be great? Because that would help us answer all the causal inference questions. And that is where our project is needed. We want to find a way for us to fill in these question marks based on generative adversarial network, which Carl talked about, and that will bring us to the answer of how to fill in the question marks today.
So yeah, the other component that is crucial to understanding our research is generative adversarial nets, GAN, the paper that came out in 2014. So how many of you are familiar with GANs, the framework? Okay, so I will give you an intuitive understanding so it's easier to understand how the framework, what makes it work. So think about a team of counterfeiters who are trying to generate fake currency. And also think about a team of police who are trying to catch the fake currency by identifying it from the real one. So they're doing classification and the counterfeiters are generating the currency, so they're doing generation. At the first, when the counterfeiters have just started, maybe they have a preliminary design which gets caught easily in the market. And then they take that feedback of what gets caught, what got them caught, and then work on the design to make better counterfeits. Meanwhile, the police is also just seeing a lot more fake currency, real currency, they're learning from this experience, so they're getting better at classification and catching. So this becomes a competition where the counterfeiters are getting better, the police is getting better, and it only stops when the counterfeits are so real-like that they're indistinguishable from the fake currency. At that point, the generation stops and the process converges. Looking at the architecture, this is made in context of a fake and real image, which GANs are mostly used for. We start from random noise or random phase, and then the generator would be analogous to the counterfeiters that I talked about in the analogy. And then we have also some real data, this would be the real currency, let's say. And then we take a sample from our generated distribution, and then we take a sample from a real distribution, the discriminator. So the police is trying to catch if in a particular image currency, a sample that we've given into it is real or not. It predicts the probability of it being real, and we calculate the classification loss. Now the essence of GANs lies in the fact that classification loss or discriminator, a classifier loss, would inform your classifier generally in any ML application. But in GANs, that classification loss also informs the generator. So meanwhile, as you improve your discriminator process, you're also just generating better fake images, so it's harder to classify them for the discriminator in the end. This is how the GANs architecture in general works. So now that we have the both components established, causal inference and GANs, let's talk about our research objective a little more. We are developing and applying a new algorithm for causal inference based on GANs. So GANs, right now we saw that they're trying to generate these image distributions as close to each other as possible. Now we try to get distribution of the potential outcomes, the treated and non-treated, for treated and non-treated as close as possible. So as we know that we need a certain conditional independence for causal inference. When we get the potential outcomes for treated and non-treated samples as close to possible or same, that's essentially translates to conditional independence, that our potential outcomes now don't depend, are conditionally independent of the fact that the sample was a treated sample or a non-treated sample. So the conditional independence that we needed for causal inference, we get through this GANs framework at convergence. So diving into the data a little bit. So our data is simulated for this process, and we are following this DGP, data generating process. Our data is simulated because, again, for causal inference, if we need to observe the theoretical results, we have to simulate data. In real world data, we cannot know the actual true ATE, ATT, ATC. So we simulate the data, we calculate the theoretical results, and then we simulate our own results, and then we compare how close they are. This is a simpler DGP for the purposes of this presentation, but we have gone to more complicated DGPs as well. The framework is independent of the data generating process. Here we can see that the covariates are normally distributed, mean 0, variance 1. Theta is a parameter that governs our generation process for the potential outcomes. Potential outcomes here are just linear combinations of the covariates with coefficients from theta with noise added. Our treatment is assigned based on the propensity scores, that is just a logic model that decides a propensity score. And the observed outcome would be in case the treatment is assigned y1 and the treatment was not assigned y0. If you do not understand this completely, that is okay, that is not essential to understand the framework, but the intuition is that we are trying to, the data is simulated because we need the theoretical results. And the DGP is designed to simulate a simple real-life causal inference real-world problem as close to the real world as possible. So So recall that generative adversarial network, their architecture looks like this. Now I'll show you how we have changed the architecture to transform it from an image generation use case to a causal inference use case. So this is how we have changed it. Instead of a random image or a random currency, we now start from a random theta. Theta, if we recall, is the parameter that governs the generation of both the potential outcomes. We start from a completely random theta, assuming no knowledge. We have the generator that will give us the potential outcomes, and we also have the observed data. So like how I talked about in the example in the first slide, in the first few slides, for every student, Jane or Joe, we will always know the score in one condition. So if a student is given the treatment, if they're given the after school program, we know their score if they were given the program. And for Jane, who did not attend the program, we know the score without the program. So the essence is that we either know y0 or y1 for all samples. And whatever we don't know, we simulate with the generator. So for Joe, because we knew the score after we took the program, we will know y1. And we simulate the y0 with the generator. For Jane, we know how the score would be, how the score is when she didn't take the program y0. And we have simulated the score for Jane, how the score for Jane would have been like if she herself would have taken the program. So this is basically the question marks that we had initially. Now we have filled them from the generator, our generator process here. And now we have for treatment 1 and treatment 0, the covariate, the actual outcome, and the missing counterfactual that is not generated by the generator. That is the generation process. Going to the discriminator. For our case here, it's a neural network. We pass the covariate potential outcomes to the neural network. The neural network tries to, again, classify and predict the probability of the particular sample being treated. If we think about the student use case, the probability of that student having gone to the after-school program. And again, like generally in GANs, we calculate the binary cross entropy loss, the classification loss. It informs the discriminator, so the discriminator, the neural network gets better. This is just back propagation. And the additional thing is that it also informs the generator here. For us, it's a Powell gradient method. And so our discriminator also gets better. This process goes on multiple times. For every iteration, we improve the discriminator. We have several iterations there. We make sure to not overfit it. And then after every few iterations of the discriminator, the generator is now trained. At convergence, the discriminator would not be able to identify if the particular sample was given the treatment or not. It will predict a probability of treatment equal to 1 as 0.5 because our simulated data is so well done that for a given sample you cannot identify anymore if the treatment was assigned or not. This may have an interesting visualization on which I will talk about.
Moving on to results, as Palak was saying about the training process, we started off here. This picture shows us the probability of predicting W, which is the treatment, for a single run, so for a single student. So as you can see, originally the discriminator is very good at telling whether this person received the treatment or not, so whether this person participated in the program or not. But after certain iterations, the discriminator and the generator both learn the discriminator learns how to tell them apart better, and the generator learns how to generate data better. And eventually, the generator generates data so well that the discriminator now cannot tell apart whether the student is in the program or not, so whether the treatment is 1 or 0. And that is why the probability eventually converges to 0.9, as Palak mentioned. So this is done only by the framework recovering the data generating process parameters data. So that means that the framework now has learned what the data generating process is, like what the data is, how to generate or how to govern the potential outcomes given the covariates from the student. And because of this, we can actually recover the treatment effects as well, because now we know the data generating process, so there's no reason why we cannot generate the missing question marks that we have seen. And we can actually do that for every single student in the program, generate the missing counterfactuals for every student, and that's how we can actually calculate the treatment effect for the simulated, which is very, very close to the theoretical, as you can see here. And I wanted to point out the last two row, which is, or the third row, where the gamma selection is not zero. And I want to talk a little bit about the gamma selection here. And that is, if you recall from the data generating process, the propensity score either depends on the covariates via the gamma selection being not zero, or it doesn't depend on the covariates being via the gamma selection being zero. And the way to think about it is that if the propensity score does not depend on the covariate, that means that the treatment does not depend on the covariate, the output. That means that the outcome for and the treatment are independent given the covariates. And that is what you would see if you have like a randomly assigned treatment, which is done in a lot of causal inference studies. However, it's not governed, it's not guaranteed in all causal inference studies that the treatment is randomly assigned given the covariates. And that's why we introduce gamma selection being not zero as well. Because in those cases, the treatment assignment do depend on the covariate, and then therefore the conditional dependence, for example, would not hold. But we see that our framework actually would be able to recover the data generating process even in those cases. And because we actually recover the data generating process, and then we can simulate the missing counterfactuals for everyone, we can not only get ATE, but we can also get ATT and ATC as well. And one other thing that I wanted to mention in our framework is that it doesn't only recover the data generating process and the treatment effects, but it also recovers the propensity score via some calculation from the discriminator output. As you can see here on the very right or your left, I think, the theoretical propensity score and the simulated propensity score have the same scale and are very highly correlated, meaning that we get very close propensity score compared to what the theoretical would have been. And if you look at the distribution of the theoretical here versus the simulated propensity score here, they are also very similar. So it shows that our framework actually also successfully recovers the propensity score on top of the data generating process and treatment effects as well.
So few of the next steps that are the extensions that we're currently working on is, we're working on more complicated DGPs. So currently we have in our theta 4 parameters. Now we're moving into a 14 parameter DGP, and some of the experiments we have done have had 22 parameters, and the covariates are no longer just normally distributed. It's a combination of uniform distribution, normal distribution, and we're experimenting with different distributions there. And more complicated, instead of linear, going to quadratic and much more complicated formulae of the potential outcomes as well. It no longer converges in 80 iterations now. The DGPs that we're experimenting with, it goes over to 2000 iterations in some cases. Then we're working on comparing results with all existing methods, majorly causal forest by EconML. That is the method that is doing the best for a similar use case now. And increasing model complexity, number of iterations like we talked about. The number of iterations just increase if we make it a complicated DGP because it just takes longer to get to the 0.5 probability. And then our ultimate step would be to try to put the framework on real data from a policy paper and seeing how our method does there. Thank you.